Hi again, everybody. Welcome back. This chapter has been on rotational kinematics, and then we've gotten into rolling motion and kinetic energy of a rolling object. Kinetic energy of a rotating object. But now we're going to be looking at kinetic energy of a rolling object, because rolling objects have two different kinds of motion, as we looked at before. If you recall my video, I showed you guys this one right here, right, where we have, oh, come on now, I'm trying to get it to play. It doesn't seem to want to play. There we go. The object is moving forward, right? All parts of the wheel are moving forward in that direction, but you have different parts of the wheel that are moving forward and backwards, like that point on the wheel right there. Okay, so we have to account for that when we calculate the kinetic energy of a rolling object. So let's go back to our main. Okay, so we're going to need to sort of establish a notation right here. Kinetic energy, this really means kinetic energy total, or T. All right, now I'm probably just going to call that K I for kinetic energy initial, or KF for kinetic energy final. But it means kinetic energy total, which is the sum of rotational kinetic energy, K sub R, which we calculated just this chapter, and also KL, that is in a straight line, linear kinetic energy. And this you know from previous chapters, that's 1/2 mv squared. This is going to be our 1/2 moment of inertia times angular velocity squared right here. So I'm not really going to indicate a notation for kinetic energy for total, but it's going to be either initial or final. Like if an object is at the top of a ramp, it would be kinetic energy initial, which would probably be 0. Or at the bottom of the ramp, it would be kinetic energy final, where it's moving. But this total kinetic energy that it has is the sum of these two types of kinetic energy that the rolling object has. It has linear motion, 1/2 mv squared, linear or translational motion, but it also has rotational motion, 1/2 I omega squared. Now, a way to sort of turn this around and kind of restate it is if we were to take this 1/2 mv squared and factor it out. Now, you know that that the angular velocity right here is really v squared over r squared, right? Or v over r squared, which really comes out to v squared over r squared. In fact, let me write it like that: v squared over r squared. That's that right there. So if you were to take if you want to try to factor out 1/2 mv squared, you could actually do that, because this has a v in the numerator right here, so that could come out, which means you would leave an r in the denominator, and then since there's no m in there, actually there's an m in the moment of inertia, but there's no m in there right now, the m would have to be divided into the denominator. And so this would become 1, that's where the 1 comes from, and then the I over mr squared would be what this turns into. So this is really saying that the total kinetic energy is the linear kinetic energy, 1/2 mv squared, you're familiar with that, times 1 plus I over mr squared. All right, so that's another way to write that, which may come in a little bit more handy for you later on. Okay, so let's do an example right here and see if we can apply this. The total kinetic energy is the sum of linear kinetic energy plus rotational kinetic energy. Okay, so we've got a 1.20 kilogram disc. So we've got a solid disc right here. That's going to be important to us. In fact, right now I'm going to just shrink this down so I have a little more space to work with. So the mass is 1.20 kilograms. All right, solid disc with a radius of 10 centimeters. So radius equals 10 centimeters, which equals 0.100 meters, right? Rolls without slipping. That's important to know. Without slipping, that means that the linear velocity that it has is, you might say that the linear velocity that it has is the same velocity that the whole system has as it's rotating over the floor or the ground right there. Okay, so it's just say it's not skidding. We'll put it this way: if it were slipping, you could say it were just spinning in place but not going anywhere. You know, like a lot of times you see in cartoons when like somebody tries to run away real fast, their legs start to spin but they don't go anywhere. Well, that doesn't really happen in real life, but that's what slipping would be. Okay, without slipping means that it is rotating and it is moving forward at the same rate. Okay, so the linear speed of the disk is 1.41 meters per second. Okay, we want to find A, the linear kinetic energy, so KL. I need to be very careful right here because I don't want that to look like a KI. But it's a KL, linear kinetic energy. All right, so that's 1/2 mv squared, and that's what we want to find out, right? And also the rotational kinetic energy, so B, K sub R, that's 1/2 I omega squared. And we want to find C, simply the kinetic energy of the disk. All right, so that's really going to be, erase that again, KL plus KR. Okay, so let's go ahead and plug our values in. So kinetic energy linear, right here, 1/2 mv squared. Well, we have all that stuff, right? A, linear kinetic energy equals 1/2 mv squared, so the mass is 1.20 times the linear velocity, that's 1.41 meters per second. Because remember, the whole object is moving forward at 1.41 meters per second. We don't need to worry about radius quite just yet. It's just simply mass times velocity. Ooh, velocity squared, right? That's velocity squared. Okay, what do we get if we key in our values? I got a linear kinetic energy of 1.19, right? Yeah, 0.19 joules. 1.19 joules. And that would be the kinetic energy if the object wasn't even rolling, but if it was just skidding forward, all right, or moving forward at that velocity right there. Let's now find the rotational kinetic energy. Oops, I just did A, do B. Kinetic energy rotational, that's 1/2 IW squared, right? Now we need to look up our I, that is our moment of inertia. All right, moment of inertia for this thing, it's a solid disk, right? It's a solid 1.2 kilogram disk. Let's look that up. So we're going to go to our table right here of moments of inertia for various different objects, and we've got a solid disk right here. The I is 1/2 mr squared, right? 1/2 mr squared. So let's go back to our problem. So 1/2 mr squared. We know the mass and we know the radius. So that's going to be helpful, right? So actually, this is something interesting you need, well, not interesting, but just something you need to watch out for. Notice the kinetic energy is 1/2 times I times omega squared. So it's 1/2 times 1/2 mr squared. So you're going to put another 1/2 in there as well. All right, so 1/2 times 1/2. What's the mass of the object? It's 1.2, right? 1.2 kilograms times the radius, that's 0.100 squared. That is our that's our I'm drawing a blank here. Moment of inertia. So this is all of our, this is our original 1/2. This is our moment of inertia right here. And then we need to multiply it by omega squared. All right, now we can calculate omega, or if we know that the angular velocity is simply the linear velocity divided by the radius, why don't we just put that in and square it? Okay? So, velocity, oh, well, in fact, let me write it over here. That equals 1/2 I times V over R, that whole value squared, right? That's what we're saying. We're saying velocity squared over radius squared equals angular velocity squared. All right, so our velocity is 1.41 meters per second. That's going to be squared divided by r, 0.100. That squared as well. Okay, that's going to be our rotational kinetic energy. So all this multiplied together is going to be our rotational kinetic energy. Let's see what we get. All right, and I've done my math. I've got 1/2 times 1/2 times 1.2 times 0.1 squared times 1.41 times, or divided by 0.10 squared. And what you probably noticed was that these probably could have canceled out, right? So it's 0.59, say, 6 joules right there. Now, these can't happen to cancel out in this problem because we have a we've got a solid sphere right here. It may not always be the case that they cancel out. So always, well, if you have to do your velocity squared over your radius squared, always just do your full math. They may or may not cancel. It really just depends on what the moment of inertia here is. Just so happens that you had an r squared in the numerator and in the denominator, and they canceled out. All right, so that is our rotational kinetic energy. The last part, which is actually the easiest, is simply the sum of those two, right? The kinetic energy total is kinetic linear. I almost said initial. Kinetic linear plus kinetic rotational. So that's 1.19 joules plus 0.596 joules, and that's going to be our total. I like to think I can do that in my head, but I'm just going to do plus 1.19 real quick. So that's 1.779 joules, which is the total kinetic energy. Okay? So we know how to find linear kinetic energy. That's easy. We've done that before. The new kid on the block, you might say, is the rotational kinetic energy. 1/2 times your moment of inertia times your angular velocity squared, or v squared over r squared. Add them up together, and that's your total kinetic energy, and that's what we get is 1.79 joules. So thanks for following along on this. If you have any questions, make sure you come ask me, and I'll help you out. But in the meantime, thanks for following along, and I'll see you on the next one.